Hi everyone, let's solve this problem. Search in rotated sorted array. So let me explain this problem. Let's take the given example. So this is the given array. So if I just copy it and get the last few elements to the front, this is a sorted array. But what they have actually done is they have rotated it 3 times in this case. So when they first initially rotate, 0 is placed at the end. Then when again they have rotated, 1 will go to the back, and then when they have rotated for the third time, the element will 2 will go to the end. So this is how the array is formed. But we are given rotated sorted array. Now we have to find the target element inside the rotated array. So if the target is present, we have to return its index. If not, we have to return -1. So, and this problem has to be solved in big O of log n. So we have to use a binary search for this. Linear search will take big O of n time. So let's understand how can we use binary search in this case. So this is our array and the above are indexes and our target is 0. So if we consider this particular array, this is our left, this is our right pointer, and this will be our mid pointer, right? So in binary search, there will be 3 cases. One is target will be equal to our nums of mid. Then we don't really have to do anything, we just have to return. Or we somehow know that our element lies on the left side of the mid or on the right side of the mid. So there are only 2 possible cases after this. One is left, one is right. Now let's try to understand it even further. So when we got mid, this is a sorted array. So if you observe, if this is the mid, this particular array is sorted already, right? At least one portion of the array will be sorted. Let's consider, for example, my mid is here. No matter what, this particular array is already sorted. I can do a binary search inside that. If the element, I know if the element lies within these elements because this is a sorted array, and I will know if I have to search in this list or I should discard this list completely, right? Or let me take a particular mid. Let's say for example this is my mid. This is not a sorted array, but the other side of it is sorted, so at least one of them will be sorted. So there are 2 lists, list 1 and list 2. At least one will be sorted. That is all we have to know. If let's say I know which side is sorted, let's say this is the mid and this entire list is sorted, so I somehow know if the target element is present in this or not. Let's say for example I'm searching for 0. If this is my sorted list, I'll check if the element lies within the range of 4 to 7. If it is not, I can easily move my pointer to mid +1, the left pointer, and search in the remaining space. But let's say my target is, instead of 0, if it is 5, I know that the target element lies within this range, so I can just like the R pointer should be less than this, and this is my search space, so I can search in this. So we just have to figure out how to get which part of either left or right, which one is sorted. That is our first goal. Once we get to know if it is sorted or not, then we will check inside the sorted list. Since we know if it is left sorted, we will check if target lies between the range of nums of left comma nums of mid. If this is the case, then I will just do my right to mid minus 1. If this is not the case, then what will I have to do? I just have to do mid plus 1, because even though this is sorted, the target does not lie within this range. So I just have to search on the other side. Similarly, if there is a way for us to know that right is sorted, then if this is sorted, our range will be, our target should lie between the range of nums of mid and nums of right. In this case, if it is the case, what are we going to do? We are going to change our left to mid plus 1. Otherwise, we are going to do mid equal to right equal to mid minus 1. That is all we are going to do. So you'll understand it better once we kind of write the code for this. So let's say left will initially be pointing to 0, and right will be pointing to nums dot length minus 1. So obviously we will be doing left less than or equal to right. And then if our target element is equals to our mid, in order to do this, we have to calculate the mid value. We are going to also take the floor of it, otherwise we'll get the will not get the integers. So left plus right by 2. So we'll get the mid, and then if it is equal, we just have to return the index. Index is nothing but mid. Else, now if left is sorted, how will we get to know? Nums of left will be less than or equal to nums of mid. Else right is sorted, right? If the left part is sorted, we will just check if target lies between left. Okay, let me. Target lies between left and mid. If this is the case, we are going to move our right pointer to mid minus 1. Otherwise, we are going to move our left to mid plus 1. So how will we know if target is greater than or equal to nums of left, and target is less than or equal to nums of mid? Then it lies within that range. That means we just have to change our right pointer to mid minus 1, because if it lies within this range, we know that we will find the element within this. So we have to move our right to mid minus 1. Otherwise, we know that it does not lie within this range, so we have to move our left to mid plus 1 so that the element can be found in the remaining list. So it would be left equal to mid plus 1. Similarly, if right is sorted, we have to check if target lies between the mid and right. If target is greater than or equal to nums of mid, and then target is less than or equal to nums of right. That means we just have to make left equal to mid plus 1. So if the element lies within this particular range, we just have to bring our left to this particular point, mid plus 1. Else we know that it does not exist in this current list, so we have to search in the remaining list. That means we are going to do right equal to mid minus 1. If we do not find the element even after this, we are going to return minus 1. So let's try to run this code. So there is some typo here. Let's run it. Let's submit it. It's successful. And similar to binary search, we are kind of dividing the list into half for every iteration. So it will be, the time complexity of this solution will be big of log n, and the space complexity of this solution is big of 1 because we are not using any extra space. I hope the solution is clear. Thank you.